events,
That's what
sinusoids.
I don't know. I mean, they're not going to see me talking, which is annoying. But
yeah,
this is not ideal.
Yeah. Also, do you need a microphone?
Well, the microphone is on the computer, so that should work. But I mean, I can't turn this video on. I mean, turn this video on, you're just going to see me. You're going to see a wall essentially, because I'm walking around here. So.
Maybe we can use just another laptop, just put it here and direct it.
Yeah, that works. That works. Oh yeah, I mean, even if you put the host. Yeah, so why don't you put your computer in like the third row or something and turn your video on? Or you turn your video and your microphone on.
but I think if I turn on my microphone as well, then maybe there will be
I'll turn mine off.
Yeah, turn off.
I'll turn mine off. You can turn yours on. It should pick me up from this.
Yeah, I think so. Maybe I can also bring my charger again.
There we go. Just make sure your sound is turned up so if anyone talks, you can hear them. Okay.
So, hello. Can you guys on Zoom hear us?
Yeah, I can hear you.
Okay, great.
And if I talk from here, can you hear me from here?
I can hear well, yes.
Okay,
Okay, great. Maybe you should speak a bit loud.
that's fine.
Yeah, because the yeah.
Are you sure? Yeah. Okay.
So this time we'll do it in this way because Alicia is not here and we don't know how to connect this PC to the cameras and
Sure.
here in this room. So hopefully this one. And I will bring my charger.
Everyone could hear and see.
Do you hear the people from the Zoom?
Yeah, we're using that laptop because we couldn't figure out how to work out using the cameras and stuff in the actual room. So we're just streaming it through that laptop. And apparently that's working. So
Okay. Good. Yeah.
Can everyone actually see the slides and read the slides, by the way, on Zoom?
We can see the slides.
Yeah. It is the maximum volume. I guess if you max out the volume.
Yeah.
System is so fancy.
Yeah, I mean, I think we left things a bit late.
Microhertz Gap in gravity wave class.
This is one of many alternative titles to this talk, but this is the one I chose. Asteroids is Microhertz Gravitational Wave Detection.
Sounds very confusing.
Do you need the extension table? You want? I have one of these.
Great.
I'm so well prepared.
Yeah. This is coming from being a seminar organizer, knowing that no questions aren't the right cables. I just had like a bag of cables that I bring.
Yeah.
I guess I could actually stop screen sharing, right? Well, actually, no, let me keep screen sharing, because then I guess people can see the slides on the screen share and can still see me on the video as well. Okay, that's good. Okay, so just there we go. Should be going.
Well, we are introducing. Okay, yeah, let's start. So hello everyone, welcome to the seminar. Today we're happy to have Michael Fedderke. Michael did his PhD at University of Chicago. Then he moved to Berkeley and Stanford, and now he's postdoc at Johns Hopkins University. And today he's going to talk about bridging the Microhertz Gap with asteroids.
Great, thank you, and thank you very much for the introduction and for the invitation to visit. This is my first talk back, since about December 2019 with an in-person audience, so it's nice to actually see faces while I'm talking again. So I'll tell you today about some work. I'm busy in the process of finishing up with Peter Graham's pseudogendron. I'm thinking about ways in which we can try and access the Microhertz gap for gravitational wave detection, and doing it in a bit of a fun and offbeat way, trying to use asteroids as test masses for a gravitational wave detector. So by way of both outline and summary of where this talk is going to be going, let me give you sort of the one-slide version of what the idea is. One of the key points we're pointing out in this paper is that asteroids end up being fantastic test masses to utilize as objects to track in a gravitational wave detector. So here are your test masses. Welcome to them. Here's 433 Eros and some other inner solar system asteroids. You're talking here about sort of 10-kilometer class asteroids, which are in the inner solar system outside of the main asteroid belt, with certain other properties that you need to make sure are okay. And I'll tell you more about what those are as I go through this talk. So these are your test masses. You're going to try and track the center of mass position of these asteroids as the traces of geodesics and GR. Now, of course, just having good proof masses does not give you a gravitational wave detector. You additionally need some way to measure the distance between them. And so the idea we're proposing here, at least conceptually, is to fly a space mission. So here's my theorist's conception of that. That space mission would deploy on each of these asteroids, 2 or more asteroids, a base station. And the base station consists of some way of measuring the distance between these asteroids, some link system and some clock system that allows you to do what amounts to something like lunar laser ranging between these asteroids. So you're just doing a direct ranging measurement between the asteroids using them as the test masses. This constitutes a gravitational wave detector. And what I'm going to be going through in this talk is basically a series of estimates for the noise environment for the asteroids, and some conceptual words about the link. I'm basically trying to get ultimately to this strain sensitivity curve, which I don't expect you to take in any detail right now, because I'm going to spend the rest of the talk getting to this point. But the idea is that we get some significant coverage in this band between, say, a microhertz and 10 microhertz. But I'm going to disappear that for the moment because I'm going to be getting there for the rest of the talk.
So you're going to get there because yeah.
That's the main result. I'm going to try and explain where we're getting to sort of give you the idea of where we're going.
Okay, thanks.
So just, you may have also seen some other recent works that have been talking about using asteroids either as fifth force detectors or trying to use them as broadband gravitational wave detectors. This is a very different idea, using a very distinct way of doing this that is not sort of the same as these other studies that have come up pretty recently. Okay, so that's sort of the idea of what it is I'm going to be talking about and where I'm going to be going. But just to take a couple of steps back and talk about, well, why? I think it's a very uncontroversial statement that we have a wide range of frequencies available to us for gravitational wave detection over many orders of magnitude here. And so this is a fairly famous plot of characteristic strain as a function of frequency, with a number of source expectations on here as well in these shaded regions. and a variety of either existing or future proposed facilities to actually try and detect gravitational waves. So not only do we have a strong science case to go after gravitational wave sources in many of these frequency bands, we also have a reasonably good coverage using, ground-based detectors have already detected gravitational waves. We understand very well how to do gravitational wave detection in the millihertz range using space-based interferometers like LISA Pathfinder already having flown. And then down at very low frequencies, we have pulsar timing arrays accessing this nanohertz range of frequencies. And these are already seeing some interesting hints of something which may possibly turn out to be a signal, although we await more data on that. The other thing which is not typically shown on this plot, but it has a lot of work's been done in the last couple of years, is the so-called midband. This is the gap between the space-based detectors and the ground-based detectors, utilizing atomic interferometry techniques or clock-based techniques. And there's sort of an alphabet soup of collaborations here that are thinking about doing this sort of thing. So there's a good science case and good coverage with one glaring exception, which is this gap down here between PTAs and LISA, where there hasn't really been much attention focused in the last couple of years. There have been some proposals here, and I'll mention some of them as I go through this, but there's been a dearth of studies here as compared to this other gap.
So could you also just remind me of say some example of new physics and the example of like a phase transition and where that would be on the spot?
Yeah. So phase transition, I think you're typically looking at these sources down here. Here, looking at sort of massive binary black hole mergers. And
so early universe is more to the left.
Yeah, but I think we were having a discussion about this yesterday actually as well. That's sort of like it does come up to high frequencies as well. So there's potential other sources at high frequencies.
So I'm thinking I'm going to get something about inflation or phase transition to 4 electron weak. It's going to be down on the left.
Yeah, it's probably going to be down this side down here somewhere.
And anything to the right is going to be more like astrophysical objects colliding.
Typically things like that, exactly. So exactly right. So actually, just zooming in on this Microhertz Gap, there was actually a reasonably careful study done here in this white paper in 2019, which is really targeting the science case of why you want to go after the Microhertz Gap specifically. So I just pulled out here a list of some of their more interesting sources here you're talking about. So yeah, it's sort of like cosmological astrophysical sources, those sort of mass ratio in spirals, which are not where the masses are not similar. But you'll notice here that sort of the strains you're trying to target to see some of these sources, so the strains you should have in mind are between 10 to the minus 18 and 10 to the minus 16 in this gap between, say, 10 to the minus 6 and 10 to the minus 5 hertz. So between 1 and 10 microhertz, you're sort of targeting this range of 10 to the minus 16 to 10 to the minus 18 in strain to actually see these. So that's sort of the target you should have in mind. So the first thing to say here is that you might think about trying to get into this band using pulsar timing arrays, but unfortunately, pulsar timing arrays don't have the sensitivity. Here's a projection for SKA, and it just doesn't have the sensitivity to get into this band for a number of reasons. So trying to get into this band, you really have to think about trying to push other techniques to get into this band, typically using the low frequency sensitivity of something which is more sensitive at higher frequencies. So for instance, here, just for comparison, is the LISA protected sensitivity. Of course, LISA doesn't reach this band because of the way it's been optimized. But you might think about other ways of doing LISA-like detection, which might be able to push you into this band. And I'll say some more words about that in a moment. This Muares study, this white paper up here, also put together what they call their straw man mission concept, which is basically a LISA-like detector, but with improvements. And I'll mention what they are. And they were projecting that if you could realize all the improvements they were assuming, you might be able to push LISA style technology down to this black dashed curve here, or this black solid curve with foregrounds taken into account. But that's a relatively futuristic proposal, so it's worthwhile thinking of alternative ways to get into this band that don't necessarily assume that those technological improvements will occur.
But that would be some satellite.
Some satellite-based things, exactly. It's all these star space-based techniques, exactly.
So when you say pulsars, do you really mean like the network of them, right?
Yeah,
So
the pulsar timing array.
This how signals propagate. But is it possible to use a pulsar itself, like an individual pulsar? Or
I don't believe it is, no.
okay.
We can discuss that more offline, though. I think it's going to take me a bit far away from where I want to go at the moment. Okay, so the other things you can try and get into this band, you can try and use astrometric techniques, looking at angular deviations between stars and large-scale survey data. I'll say some more words about that. I'll show you some projections for that. Typically, they only end up getting these strains which are quite a bit higher than you would need to see some of these interesting sources. So it turns out, I think the summary here is, it turns out to be singularly difficult to actually build detectors that work in this band. And I just want to spend some time talking about how it is these space-based detectors actually work at a very conceptual level, and why it is that this is difficult to go into this band using these sorts of detectors pushing you to low frequency, because that will lead me quite directly into talking about why asteroids are interesting. So let's think about space-based gravitational wave detection, local test-based gravitational wave detection 101.
Can we slow down a bit? Can we move back 2 slides just about Tony's question?
why do we motivate this rate, right? When people talk about strong first order phase transition happening at TeV scale, for instance, the frequency band is the first level, or
Yeah, sure. That's why I said this you can also push up to high frequencies here as
yeah.
well.
So we in my opinion, we shouldn't say that this gap is covering some unique region that phase transition like to public.
Oh no, I'm not making that claim at all. I'm simply saying, two big things basically. There are known sources which exist in this band. There are potentially other things which exist in this band, and we also don't know what's there until we look. So we should definitely just try and look, because it's a new frequency band we have not looked in before, so you don't know what's there until you go and actually try and see what's there.
Sure.
Yeah, but following on Jean's question, I mean, is that band, is it going to be sensitive to like a phase, strongly first order phase transition at TeV?
I would need to look up the numbers there. I don't have to.
Oh,
Yeah, but actually that peak frequency is at the millihertz level. That's the other part. Yeah.
So anything below millihertz is
So it's a in a good approximation, it's proportional to temperature. The universally proportional to the peak frequency. But that is quite an approximation. That's don't get into that. I'm just saying, depending on the nature of phase transition, you're probably in different frequency.
Yeah, sure.
so you can populate that whole plot.
Yeah, but they have different density in some sense for typical phase transition.
Yeah, so it's probably going to be some, it's very some curve on here which will tell you like where you expect the phase transition to lie. Yeah.
Can I go back to that slide? Go back one. You can make this plot, but why did they put the stochastic background in this argument?
This is the plot I got from the internet. I mean, I don't want to spend too much more time on this because this is more sort of motivational stuff rather than actually what I'm going to be talking about. So I'm just presenting this as this is a well-known plot for sources. Let me move on to talking about this.
Can I go back one more slide? Something you went through quickly. You say there's other recent works that I'm aware of that also using asteroids to test for fixed force or other stuff.
Yes.
You say you're quite different.
Yes.
I guess first they are fixed force. They are really checking the distortion, static distortion.
Yeah, they're looking at orbital deviation, specifically the
Right,
precessional semi major axis of the orbit. Yeah.
Yeah. So you're looking for gravity wave, so it's a totally different time.
But I mean, in principle, you can utilize the same techniques they were using to go for gravitational waves as well. They just didn't in that paper. But in principle, one could think about doing gravitational wave detection using the approach they were taking. But this is a very different approach because we're doing direct ranging. We're not doing astrometric detection of asteroids.
I want to comment on the comparison.
Not further. I mean, no.
Okay, maybe
let me get to where we're going with what I'm actually talking about. Yeah.
But don't worry if you go over.
Okay.
We're flexible here.
Okay.
Don't worry. Don't think you have to rush to finish it.
All right.
Yeah, that's right.
So don't worry, because there'll be a little.
Okay.
Yeah.
Don't worry.
All right.
So can you comment on when they do gravity wave, how different from yours? Okay.
So the one that actually has looked at gravitational waves here, I forget exactly which of these two papers it is. I think it's I believe it's these two.
Okay.
This is Diego Blas and Alexander Jenkins. They were looking at thinking about the perturbations to binary system orbits and asking whether or not there's a perturbation from gravitational waves, a broadband background of gravitational waves on binary orbits, because you will find in a broadband background, some frequencies will overlap with resonant frequencies in the orbit, and that can cause orbital distortions. So depending on which systems you're looking at, they have a sort of a summary plot which says, like, in this frequency band, you can look at this system and maybe get some ability to detect gravitational waves at a certain sort of broadband level. Trying to use those detectors for narrowband gravitational waves is tricky because you have to then say, okay, my narrowband signal happens to be exactly coincident with one of the resonant frequencies of the system, which is of course very unlikely because these things are quite narrowband, right? So the two proposals that were there were looking at basically just like distortions to binary orbits.
Binary of what? Binary of.
So a variety of systems, right? Millisecond pulsars that are in binary orbits. I believe one of the things they were looking at was lunar laser ranging.
But not asteroids.
Not asteroids in that particular case. The other one that has actually used asteroids, but for the full search, so you're correct, it's the DC signal. It's just an additional contribution to potential, which causes an orbital precession. That was just looking for orbital precession of a small number of asteroids that have been tracked that pass very close to the Earth, because you get the most tracking sensitivity from, say, like Arecibo when it existed, as those asteroids do a close pass near the Earth. So you can get the most resolution on the orbital track as it comes past the Earth. So there were projections in that paper as well for how what you could do with if you could track similar numbers of asteroids elsewhere in the solar system, although that might be more tricky because you don't have things like Arecibo available to you if you're tracking an asteroid in the outer solar system, right? So they were basically using, very different techniques, thinking about sort of the large scale orbital data of the system rather than utilizing asteroids themselves as test masses and ranging between them.
Yeah, thanks for explaining.
Okay.
Now I'll just make your later comment.
All right. So where did I get to? So we were talking about, okay, space-based gravitational wave detection. So the idea here for local test mass-based gravitational wave detection in space, which I'm going to refer to various ways, this is LISA style detection at least. The idea is you have some object inside your spacecraft. It's a metal cube. In LISA, it's a 2 kilogram gold platinum cube. You try and fly your spacecraft around that test mass to shield it from all environmental perturbations, and you use this thing as a tracer of a geodesic in GR. And then you fly 2 or more such spacecraft, here shown by A and B, and then you do some version of ranging between the test masses inside these spacecraft. At the most basic conceptual level, you're just literally measuring the light travel time between the spacecraft. And if a gravitational wave comes in and perturbs the space-time between the 2 spacecraft, that will show up as a cosinusoidal fluctuation of the light travel time or the proper distance between these 2 test masses. And that's the thing you're looking for, is this AC oscillation of the distance between these 2 test masses. Now, of course, the way that LISA actually does this is way more sophisticated than this. This is the sort of very straightforward conceptual level idea. But this is sufficient information to understand how this idea works, to understand what the limitation is at low frequency and why it is pushing this technology to low frequency is actually quite hard. So let me spend some time talking about that. So what really limits your low frequency sensitivity for all these detectors is not how well you can measure where the test masses are, it's how good the test masses are as test masses. You basically can't isolate test masses from their environment perfectly. And doing this at lower and lower frequencies becomes harder and harder. At 10 to the minus 6 hertz, the period is 10 days. So you're trying to isolate a test mass completely from its environment down to an extremely low level of perturbation for a 10-day period. That's very hard. All right. So these characteristic strain sensitivity curves that I showed you for, say, LISA, all have this sort of bowl-shaped structure. The high frequency end of this is dictated by how well you can measure where the test masses are, but the low frequency stuff is all dictated by acceleration noise and how well the test masses behave as test masses. So just to give you an example of this, let's look at LISA Pathfinder, the technology demonstrator mission for LISA. So LISA Pathfinder was a resounding success, right? So here are the results for the so-called amplitude spectral density and acceleration. This is the square root of the power spectral density. So you look at the acceleration time series, you take a Fourier transform, you square it, put some normalization factor in front of it and take the square root. That's what you're seeing here, the ASD. And this is the requirement that LISA imposes on the test masses in order to be able to build LISA at its design sensitivity. The red line is the LISA Pathfinder results. This is a resounding success for LISA Pathfinder. And so in particular, you'll notice that LISA is optimized here to work between 1 millihertz and 10 millihertz, really good results there. But as you move below the band where LISA has been optimized to work at 1 millihertz or so, you see this rising 1/f noise, sort of like pretty universal scaling for noise is 1/f. And the reason you see this kind of thing in LISA Pathfinder is because of like very, very subtle effects. Your vacuum inside the spacecraft isn't perfect. So every now and again, a gas molecule pings into the test mass and causes its position to move. Or the test mass can be charged by cosmic rays passing through the satellite, and then any stray electromagnetic fields will then act on the test mass and cause it to move around. And there's some technical noise sources as well. But when you combine all this up together, you get this rising 1/f noise, and when you combine that with an expression for how you can translate this to characteristic strain, it turns out this cuts off your sensitivity and characteristic strain as a very sharp power law of f to the minus 5 halves. So as you try and push, if you took LISA itself, as LISA has been optimized, and tried to push this down to microhertz, the strains you're sensitive to are way too high for our interest for what we're trying to do here, right? But of course, that's not a criticism of LISA in any way. That's just because LISA has been optimized to work at 1 millihertz, whereas we're trying to do this at meicrohertz. So the question which naturally arises is how could you improve this? And that's what that Muare's technical strong emission concept was basically trying to get into. Basically asking the question, how do you improve this? So the one thing they did immediately was say, well, of course, LISA uses a 3 gigameter arm length for their baseline between the 3 satellites in their constellation. Why don't you just make that bigger? Because the characteristic strain sensitivity scales down as the length of the baseline for a fixed acceleration noise on each test mass. And so if you use something which was 100 times bigger, so you have 2 AU distances between your test masses, you can win 2 orders of magnitude on the strain noise. So that was their first assumption. And the second assumption they made was just an improvement in the test mass isolation. So what they were assuming in that black dash curve that I showed you a couple of slides ago was that you can take the best measured noise level at LISA Pathfinder, actually slightly better than that, and extrapolate flat in frequency to low frequencies without the rising 1/f noise. Now, you can judge for yourself whether or not that's technically achievable, but the unambiguous statement is that at 10 to the minus 6 hertz, that corresponds to at least a 3 order magnitude improvement in the acceleration noise isolation as compared to the extrapolation of LISA Pathfinder to lower frequencies. LISA Pathfinder itself, by the way, that's the last data point there, and it's actually at 2 times 10 to the minus 5 hertz. So that was what that MURS study was assuming. So you could both have larger baselines, which is technically challenging for the orbital insertion requirements, and you have increased test mass isolation engineering as well. But given that you have to do reasonably extreme things here to get sensitivity, it's worthwhile thinking about other ways to try and improve this. And one of the things you can obviously try and do is make your test masses more massive, because for a fixed force on the test mass, of course, the acceleration is inversely proportional to mass. So if you make your test mass bigger, you could potentially also cut down some of these noise sources. But unfortunately, there's a limitation to how large a test mass you can fly from the ground, because you've got to put it on a rocket and send it into orbit. And so, you maybe can go a bit bigger than 2 kilograms, but you can't go to something which is an asteroid mass. And this is what leads us into thinking about asteroids, right? So,
sorry, before going,
yeah.
Could you just comment on the time scale of this new Earth?
MURS, okay, there is no time scale from MURS, because MURS was literally, here's what you would need to do to get access to this band using LISA style approaches. Okay. That's the level at which that study is set up.
Yeah, I mean, LISA is already like the next big year, right? So
LISA, you're talking about mid-2030s, I think, for actual data. MURS is it's a conceptual technical study at this point, just basically a straw man saying you would need to get here to get that sensitivity.
That's 2 AU, right? So that's way out.
Yeah, it's a little bit, yeah. So you do need very long baselines. That makes the orbital insertion characteristics quite hard, because you already have to pressure fly LISA at 3 gigameters. Now trying to do the same thing at 2 AU, you're going to be 100 times better on your orbital insertion characteristics to not get a big relative velocity between them.
I see.
Which is relevant for LISA, but not for us.
So one of the reasons we moved to space is we want to get rid of seismic noise, right? And seismic noise is 1 over f scaling. So should I be surprised that when you are into space, you still have a 1 over f noise coming from other sources? Oh yeah, because this is stochastic, Brownian motion of residual gas, right? I mean, 1 over f is a fairly typical scaling for this sort of random process. Yeah. I can't give you a reason why it's 1 over f, but it is. Of course, I can make an analogy. Okay, so your whatever holding you is like it's shaking is. Well, there is no shaking. There's no issue with the test mass being held. The test mass floats freely inside the spacecraft, at least on the sensitive axis, right? So it's not a sort of direct coupling or vibrational motion of the spacecraft. This is literally just the fact that there's not a perfect vacuum inside the spacecraft. So there's like residual gas molecules stuck to the surface of the test mass when we put it in orbit, and they're outgassed and then ping around inside the spacecraft. But it is disappointing that I have this 1 over f noise dominance very quickly. Right? Yeah. Even if I move from Earth to space. Yeah. Yeah. All right. So this idea of going to larger masses sort of leads us quite directly to asteroids, because I think the statement is that no one has demonstrated test masses that work at the level of isolation you need at a microhertz. And so it's worth thinking about other optimization choices you could make here, right? So for instance, the question which naturally then arises is, okay, well, if you can win by going to a large mass object, can you find some existing large mass objects that you can utilize as test masses? So sort of in some sense inspired by pulsar timing arrays, because they're using essentially the fact that a pulsar is an extremely massive object that's very hard to perturb externally. So the idea we're going to try and exploit is trying to see, can we find some natural astrophysically massive test masses that you might think, okay, go for the largest mass object you can find. But I want to do this in a way that I get to deploy the ranging link, because we can build pretty good ranging links between the objects. And that's actually one of the reasons that pulsar timing has difficulty getting into the band we're talking about, because you have a fixed ability to measure the residuals on the pulsar pulses because of fixed, limited statistics from the pulsars. So we want to try and engineer the ranging link because we know we can build ranging links that work very well at these frequencies, but we just need better test masses. And so that sort of relatively uniquely, although potentially you can use moons as well, leads you to thinking about asteroids as the test masses, because these are much more massive objects you can fly from the ground, but they don't have atmospheres like planets, and they're accessible to us to be able to deploy ranging links on them. Moreover, they are much more massive than things you can fly from the ground. These are 15 orders of magnitude more massive than the LISA test masses, at least the ones I'm going to be thinking about. And you naturally get the long baselines between asteroids because they are typically separated by an AU when they're in the inner solar system. But the downside is that I'm going to give up completely on trying to shield these things from the environmental noise and just evaluate the environmental noise that you find in the space environment, and just say, given the environmental noise that asteroids suffer, do you win by making this optimization choice of going to a large mass object with a large baseline, but just take the environmental perturbations, or is this not a win? And it turns out it looks like it is a win.
But how do you know all the environmental noise is not out there?
Right, I'm going to walk through a long list of things we've estimated.
The one could be something that you don't know, right?
Oh, there's always that. There's always a possibility of something we don't know. Yeah, I mean, sure. We've thought long and very carefully about this, and I think we've identified the dominant noise sources. And you'll see in a moment what they are. And I think if these ones aren't a problem, I would be surprised if there are others that are a problem. Yeah, you'll see when I walk through what they are, that I think we've covered the big ones.
And the unknown noise has to give you an AC signal, right?
Yeah.
Mimic a vacuum. I think that's theory of a lot of rather static.
Yeah. So before I get to the evaluation of the environmental noise, let me just briefly say a bit more precisely exactly what the setup is here, just to remind you what I'm doing here. So, the asteroids themselves are the test masses, right? So you would identify some inner solar system asteroids. This is 433 Eros. It turns out to be a really good candidate because it's in the inner solar system. It's got a 4 or 5 hour rotational period. It's 16 kilometers in diameter. It's got a very large mass as a result of that. It's got a low magnetic moment. For any number of reasons, it's a really good candidate for this idea. And
this cigar astronaut,
yes,
people will think that aliens made that.
No, that's a comment. That's a
This is not the lobe.
No. It looks similar in shape, but it's not.
Does that look like a spaceship?
This is the one that was landed on by Neil Shoemaker, actually.
Ah, okay.
So it's been very, very well studied. So Eros is a really good candidate for this. We have a list of other potential candidates, but none of them have been as well studied as Eros. So I'm just going to put up another asteroid here that has a nice picture. This is Bennu. Actually would not be a good candidate because this thing is actually an unstable rubble pile that actually throws rocks off its surface as a result of its rotation. So that kind of asteroid is not what you want to go for. You want something which is more stable, but it has a nice picture. Okay, so now you've identified some asteroids, and I'll show you a list of some later. You engineer, build, and fly this ranging link, which you would deploy on at least 2 asteroids. And the ranging link consists of 2 components. The first one is some sort of electromagnetic emitter receiver on both sides of the baseline. So that can either be a laser system or a radio system. And the idea with that is you can send pulses from one asteroid to the other using that system. And then you're going to do some sort of ranging measurement by sending pulses back and forth and measuring the travel time between the pulse going out and coming back.
And don't they have to be oriented?
Yes, they do.
And how do you slow down the rotation?
There are a number of ways you can think about doing that. Let me defer that question to when I actually talk about the link system. I think we'll come up more naturally there. There are a number of potential ways you can think about actually implementing this link system. You don't actually have to, let me say at the moment, you don't necessarily need to land the base station on the asteroid surface itself. You can get away with putting a lot of the link system and clock in orbit around the asteroid and then referencing that satellite to the asteroid surface using something like corner cubes. So you can kind of get away with the pointing doing that. This is getting way into the technical weeds of this, though. We're doing this more at a conceptual level. So so one part of the base station is this electromagnetic system, which allows you to send pulses back and forth across the baseline. And the other part of it is a really, really good clock that you need to be able to measure the light travel time between the pulse going out and coming back. And it turns out this clock needs to be as good in fractional frequency stability as the characteristic strain you try and look at. So I'll say some words about that toward the end. But this is the idea I'm going to try and evaluate. Okay, so the initial things I just want to say. So I've already told you 433 Eros is a really good asteroid because of its properties. There are a number of other potential asteroids you could think about looking at. Here are just some of them. These are also asteroids that are sort of in the inner solar system with 10-kilometer diameters. Rotational periods no longer than a few hours, so that the rotational motion has a frequency which is actually above the band we care about at 30 microhertz. And we know Eros is a low magnetic moment, which is relevant to one of the noise sources. We don't really know exactly what these ones have for their magnetic moments. That would be something you would need to identify, but at least, potential asteroid candidates are not incredibly numerous, probably a good thing for the long-term existence of human civilization on Earth, that there aren't a lot of 10-kilometer asteroids flying around in the solar system. But, there are a couple of them which could potentially be candidates for this. The other thing is, of course, is that, this idea of landing stuff on asteroids might sound a little bit science fiction the first time you hear about it, but this has been done a couple of times in the last 20 years. This is sort of a relatively exhaustive list of the missions that have actually visited asteroids, where they went. See, one of them actually visited Eros, and then what they did. So they've either orbited or landed on them. In one case, actually deployed little hopping rovers on the surface. That was High Energy 2. And then if you direct your attention to this little picture at the bottom of the slide here, we actually did a sample return mission from the surface of Bennu with Asteroids. So that's actually Asteroids crashing into the surface of Bennu and picking up a sample from its surface.
That was the Japanese.
This is the NASA European, I think this is the NASA one. Hayabusa is the one from the Japanese Space Agency. One of the two.
The one that returned the sample already to the Earth and then moved to another asteroid.
Yeah, that's, I believe that's one of these two. Yeah, here's sample return, yeah. I think the one that's still going is this one here. This is why I have this ongoing here. This is the other one that's going on to another asteroid now as well. And then this is the comet they landed on. So this is obviously not an asteroid here, but they did that on a comet as well. Okay, so asteroid candidates exist, missions to asteroids are ongoing. So that sort of passes the existing sort of smell test, at least for the first sort of zeroth order stuff, to make sure this is sort of not a completely mad idea. But of course, doing that and actually sending a mission to an asteroid and deploying base stations is only worthwhile if I can demonstrate that the environmental noise is actually low enough to make this a worthwhile prospect. So we've gone through, as I said earlier, a lot of things we've checked for asteroids. And I'm not going to go through all of these because some of them are not that relevant, but the ones that are relevant are the ones that I'm going to go through, which are the ones in blue here. So sort of pretty big things like the solar radiation pressure on the asteroid and the fluctuations in that. And I'll walk through estimates for each of these noise sources, also magnetic torques. So the rest of the talk is going to split itself into two parts, basically, one of which, the larger part of which is going to be me talking through all of these noise sources that are shown here in blue. And then there's sort of a separation here between the asteroids being good test masses and how good your link system is and the ranging system. And so toward the end of the talk, I'll say some more conceptual words about that link system and come back to your point as well about exactly how you can do some of these technical things as well. So let me just jump in with the estimates of the noise sources. Okay, so before I get there, let me just orient ourselves to the parameter space I'm going to be looking at. This is characteristic strain of 10 orders of magnitude, frequency of 5 orders of magnitude. Just to orient ourselves, here's the LISA L3 design sensitivity proposal. This is this Juarez technical design study. Well, I should say strong emission concept, not technical design study. It's a strong emission concept from Juarez. Here are some existing pulsar timing array limits. And then here are the astrometric things I was talking about earlier. So here the idea is that in large-scale survey data, you're looking at the angular fluctuations between stars. And although your angular accuracy with any pair of stars is not great, over the entire data set, you can potentially pull out the gravitational wave signal. And these are projections for both Gaia and Roman Space Telescope survey data looking into this band. So you can see you do get some access to this band in the frequencies we care about, but the strains are at higher levels than we want to get it to. Because I remind you, the target is this box down here, which is 10 to the minus 16 to 10 to the minus 18, between 10 to the minus 6 and 10 to the minus 5 hertz. So we're trying to get in here, and these wouldn't allow access to this level of strain down here.
So maybe I didn't catch it. What's the Roman EML? Did you mention that already? Or?
The difference between the two?
No, what are Roman?
Oh, Roman is the Roman Space Telescope. This is a future survey, sort of similar to the Gaia astrometric survey. Okay. That amount of sort of data, you're looking at just angular positions of a very large number of stars.
Because they resolve into the higher frequency, means they look.
I believe it's the cadence of the measurements that matters there, right? So it's how often you revisit the same stars. This is also one of the reasons pulsar timing arrays, you're limited by your upper frequency sensitivities, how often you can revisit the same pulsars and see where the pulses are.
So I think they have much higher sampling rate.
I'm guessing that's the reason. I think because Roman Space Telescope has a larger mirror, I think. Okay. So this is the parameter space I'm going to be looking at for the rest of the talk. So now let me start going through some of these noise estimates and knocking them down. So the first one, of course, you might worry about is the solar radiation pressure acting on the asteroids. This is obviously like a really big perturbation the asteroids suffer. And if you make an estimate just of what the DC acceleration is on the asteroid from the solar radiation pressure, if you take an Eros class asteroid, something 1.5 AU from the sun, 8 kilometer radius, actually this is the density of Eros. I'm just assuming a spherical asteroid for this estimate. So, obviously there's auto and geometrical factors here, but the acceleration that comes out of this looks small, 10 to the minus 14 meters per second squared. But when you remember that this thing is acting over the gravitational wave period, which is 10 to the 6 seconds, that DC acceleration moves the center of mass by a centimeter, which on an AU baseline, and AU, I remind you, is 10 to the 11 meters, would give you a strain of 10 to the minus 13, which is 3 orders of magnitude too big, at least 3 orders of magnitude too big to enter the band that I'm actually interested in. So if this were the right noise estimate, I wouldn't be here giving this talk. But of course it isn't, and for the reason that was already mentioned, this is the DC noise estimate, of course, and the gravitational wave signal is not a DC signal at these frequencies, it's an asymmetry signal, so the DC acceleration is not the relevant noise. So you have to go back to this expression, forget about this that I just told you about, and look for time dependence in that expression, right? So there are at least 3 things that depend on time here. The first one is the cross-sectional area, and this is a folding together of the actual geometrical area with the albedo of the surface. So it's some sort of effective cross-sectional area presented by the asteroid to the incoming solar radiation flux. That, of course, modulates typically at order 1 because objects like asteroids are not spherical in general at the orbital period of the asteroid. At the rotational period of the asteroid. The rotational period of the asteroids we're talking about here are going to be carefully selected to be above the band we care about at 30 microhertz. So this is a 4 or 5 hour rotational period. Actually, it's a bit higher than 30 microhertz. So the rotational period noise the modulation of the rotational period from this cross-sectional area changing is an out-of-band noise source to the high frequency side. And typically you won't get leakage of this down to lower frequencies because you're not going to find lower things than the orbital frequency, the rotational frequency. You will find higher harmonics, but the rotational period itself is probably going to be the lowest frequency noise source that comes in from that modulation. The other thing, of course, that modulates as a function of time is the distance of the asteroid to the sun itself. This modulates typically by 30 or 40% around the orbit because asteroid eccentricity is about 0.3 or 0.4. But so of course that's going to modulate this acceleration at the orbital period, but the orbital period is on the low frequency side because orbital motion in the solar system is at 1 to a few years, corresponding to frequencies below 3 times 10 to the minus 8 hertz. Now you will get some leakage of the higher harmonics of that motion into sort of at 2 higher frequencies. But by the time you get into our band, it turns out because these eccentricities are not that large, the harmonics get exponentially suppressed in their actual frequency overlap and the frequency content of the orbital modulation of this distance gets exponentially suppressed because essentially every high harmonic comes with another power of eccentricity sitting in front of it. And so you can very rapidly see how even 0.3 to a large power gets very small very quickly. So there's an exponential suppression of the harmonics of the orbital motion as well. So this is also not a relevant noise source. But the thing that is actually a relevant noise source is the sun itself, because the sun fluctuates, the sun's power output actually fluctuates in this frequency band. And that's been measured. So you can utilize this expression up here for the acceleration and just convert then the fractional power spectrum fluctuations in the solar output to the acceleration up to spectral density. And then you can use this to convert it to a characteristic strain. And I'll say some more words about the approximations that go into this in a moment. But let me show you what the results for this look like when you actually go ahead and do this. So here is the solar power spectrum, the fluctuation solar power spectrum taken from this paper down here. If you can't quite see here, this is 10 to the minus 6 hertz. And it's reasonably flat below that, and then drops off pretty rapidly above that. You'll see in the red data here, a very strong peak at the 11-year solar cycle. And then these other 2 lines here are shorter segments of data taken for sub-solar cycle periods. And so that's why the noise level sort of fluctuates up and down between the blue and green band, because you're looking here at sort of different periods during the solar cycle. This motion gets sort of put into this frequency band when you're actually thinking about a longer period time series. But if you just take these results and plug them into this expression up top here, taking some assumptions about the asteroids you're talking about, you get this variety of red and brown lines here, one different color line for every one of the different power spectra you get. And you can see that this is a very low level of noise. It's lower than the noise level we care about, which is this band right around here, this area right around here. So the assumptions that underpin this line are that I'm talking about for the purposes of these estimates. These are not supposed to be taken as order 1 accurate estimates for any particular asteroids in the solar system. This is supposed to be a sort of order of magnitude estimate for the noise level that you would see for this class of asteroids. So I'm assuming here 8-kilometer radius spherical asteroids. I'm assuming they're pinned at 1.5 AU from the sun in distance, and I'm assuming they have a pinned 1 AU baseline between them as well for the purposes of drawing this plot. But of course, the fluctuation in all of these things is out of band for this frequency band we care about. So this is the right noise estimate in this frequency band. But of course, it would be subject to corrections once you go too far out of this frequency band. But those are the assumptions that underpin this line. And you can see already, this is one of the, what you might expect is one of the larger noise sources, and it's low enough that it's not a problem for us.
Are you saying you can do better than this plot?
No, what I'm saying is that there are, if you wanted to evaluate the noise at 10 to the minus 8 hertz, you would start need to take into account some of these additional variations.
I meant in this microhertz band.
No, I mean this is going to be a noise level. You're not going to be able to beat this. I don't think. Yeah.
Yeah, but you're assuming, I thought you said this was a curve for a generic asteroid. So you're saying that if you, maybe a particular asteroid will be better or worse?
Oh yeah, okay. But by an order 1 factor. It's not going to be a dramatic difference unless you find something very, very big. But the very big asteroids are in the asteroid belt, and there are other noise sources that are associated with being there. Yeah. I mean, in principle, you could actually, you could in some sense try and account for some of this by actually monitoring the solar output on the satellite that's on your asteroid at the same time.
Yeah.
But you also need to have a very good model of the sulfur albedo of the asteroid, and so maybe you get 1 or 2 decimal places on that, but you're not going to get rid of this completely. Okay. So that's solar intensity. The other thing the sun, of course, does for you immediately is a solar wind. This is a stream of charged particles flying out from the sun, typically protons, electrons, and some heliums with some trace high elements as well. The speeds of this are typically 400 kilometers per second. That's actually reasonably flat all the way out to heliopause. It's being measured by the Voyager mission to be about 400 kilometers per second all the way out. The number density near the Earth is 5 per cubic centimeter, and that's been measured to fall off as 1.r squared. Now, why I care about this is because a stream of charged particles smacking into your asteroid gives you a dynamical pressure on the asteroid surface because they scatter off the asteroid. And that means that fluctuations in the solar wind, which are in band, are going to give you a fluctuating dynamic pressure on the asteroid, which is going to give you a very similar noise source to the solar radiation fluctuations in the same band, just with a different expression for what the pressure is. And the relevant conversion between properties of the solar wind, which is the number density times velocity squared, and the acceleration entropy spectral density are shown down here. And we can use real-time monitoring data from the solar wind from the SOHO satellite. Here's 23 years of it. And you can just take the direct power spectrum of these fluctuations in both the number density and velocity and convert this to what the power spectrum is in the relevant frequency band we care about. When you do that and make the same approximations about the asteroids you're talking about as I already did for the solar intensity, you get the green band, and the green line being sort of a smooth version of the green band. So once again, we still have access to the region we care about here. This is again a low enough noise source, we don't worry about it. I should say both that for this estimate and for the solar radiation pressure, I'm showing you the results for the center of mass fluctuations. You might also in principle worry about torquing or rotational motion on the asteroid, because there can be differential albedo between the left and right sides of the asteroid, the top and bottom of the asteroid, or the shape changes, so it looks different in terms of its response to the pressure being applied. But there's a fairly general purpose argument that I can show you afterwards if you're interested, just to tell you that the torques are no worse than the center of mass motion. So this is going to be no worse than this will be the additional rotational perturbations, and typically they'd be suppressed as well. Okay, so those are sort of the two pressure things. The other thing the sun, of course, does for you is heats and cools your asteroid. So this is going to give you a fairly enormous signal on the rotational period of the asteroid, because asteroids vary between like minus 100 Kelvin, minus 100 Celsius and a couple of hundred Celsius as they rotate around. The light and dark sides of the asteroid have a couple of hundred Kelvin variation in temperature. And so, there's going to be a lot of noise right at the rotational period, but because you're measuring the distance between the asteroids by using objects that are located on the surface of the asteroid, there's already a large noise at the rotational period, which is just the orbital motion of the asteroid, which is going to be something you can't really look for a gravitational wave signal at the period of the rotation of the asteroid. So if there's additional noise at the rotational period, I don't really care about that. What I care about is a more subtle effect, and that is that because the solar output is fluctuating on longer timescales, it will modify the equilibrium temperature that the surface of the asteroid can reach under solar heating. So the surface temperature of the asteroid is fixed by a balance between incoming solar radiation and outgoing re-radiation from Stefan Boltzmann re-radiation from the surface. So if the solar power fluctuates, so does the asteroid temperature. So what I'm saying here is that the solar power fluctuates, which we already know it does. There will be a modulation of the maximum temperature fluctuation that can possibly occur, which is the equilibrium temperature fluctuation of the surface of the asteroid on the same frequency timescale, or same timescale, sorry. But of course, this is a boundary condition modulation. This is not like the entire asteroid is heating and cooling by this amount. Only if you look at how the heat will actually propagate into the asteroid using the heat equation, you can actually figure out that only about the upper meter or so of the asteroid, maybe less than that, could ever possibly be heated and cooled by this amount. And actually, this has been backed up by in situ measurements made on the moon during the Apollo missions. They actually drilled into the moon and measured the heat flux in the lunar down below the lunar surface, and they found there was no measurable heat flux below 0.5 meter below the surface of the moon. So this argument has been backed up by actual in situ measurements on a body in space. So you might ask, well, why do I care about this? Well, again, it's because your base station over here, this little dish, is sitting on some now, say, meter thick region of soil, which has this temperature fluctuating by roughly this amount, and then below it is not moving. So if this upper meter or so heats up, your base station moves up. If it cools down, your base station moves down. And of course, because you're using the base station as a proxy for where the center of mass is, that extra fluctuation corresponds to a noise on the strain measurement as well. You can work out how much this thing moves using thermal expansion properties of the kinds of rock you're talking about here, and then convert that to a strain noise. When you do that, you get this series of pink and purple lines for the same assumed asteroids that I was talking about earlier. So once again, low noise level, maybe some higher noise at higher frequencies. Don't necessarily trust this all the way out to high frequencies here, because of course the rotational periods are starting to enter over here, but at least in this band over here, again, this is a noise which is low enough we don't worry about it.
Thermal noise and solar noise are somewhat correlated, right?
Yes. This power spectrum and the one that goes into drawing the brown and red lines are the same solar power spectrum, so the conversion between the two is different.
Can you use this somehow to eliminate it to certain extent?
In principle, yes. I mean, I think there's always a statement here that some of these effects can be modeled out to some level. So maybe you can get an order of magnitude better than this. You can fit this out to 1 decimal place or something like that. I think it'll be a challenge to make an argument that you can do much better than this, because the modeling you need to do is to say, for that case, you would need to be able to say, given a perturbation from the sun, can I tell you exactly how the entirety of the surface of Eros is going to respond, so that I know how my point on the surface has moved relative to the center of mass. You can presumably do that to some level, but doing it to more than 1 decimal place might be challenging.
Yes, so why do the curves have all this? Is it just because you do randomizing?
No, this is because I'm doing a direct translation here between the solar power spectrum fluctuations and these noise estimates. And I remind you, the solar power spectrum actually has these fluctuations in it, just from measured data. So you should take a sort of a smooth line through this, I think, actually.
Sorry, just to make sure, you said that we dig into the moon and measure the temperature fluctuation. There's no observable. How deep we dig into it?
This was 0.5 meter from the surface.
When you do this astronomical equation, why don't you just put your station tight?
Yeah. Okay. Yeah. Good. Yeah. Good. So that's something I didn't mention here. In principle, if this were a problem, you can do exactly that, right? You can drill into the surface, and then, although your base station might move around, you can reference the base station position to a point inside the asteroid that isn't moving around as much. Maybe you drill a hole and you laser range to the bottom of the hole, or something like that.
Yeah.
So you can
in the deep there.
Yeah. You can mitigate it, but the point is you don't need to, right? This noise level is already lower than other noise levels which are larger. So you could mitigate it, but there's really no point of mitigating it, because it's okay. Maybe up here it's a bit higher, but you'll see in a moment that this region is also sort of subsumed in other noise estimates as well, like the range link. So yeah, sure, you can mitigate this by doing that, but you don't necessarily even need to.
Sure. But just a very dumb question. The moon has dirt on it, but asteroid has dirt or not?
It depends on the asteroid you're talking about. If you remember that video of Bennu, actually when the thing crashed at the surface, there was like a cloud of rocks that flew off the surface. So yeah, that was like rubble on the surface. That actually helps you because that cuts down the thermal conductivity. Because that's one of the reasons that you only see heat flux at 0.5 meter in the moon's surface, not the meter I was estimating here, is because there's this blanket of regolith, which is sort of a couple of centimeters thick on the lunar surface, and heat doesn't conduct as well through sand as it does through solid rock. So that sort of helps you. In that case, the kinds of asteroid missions you would actually would want to anchor to something more rigid below the asteroid. So you may have to do some sort of digging below the regolith to actually get there. But yeah. Okay. So those are the 3 things from the sun. Then I was saying, there's noise at rotational periods. So where would that come in? So these are just a couple of bands, the sort of fundamental and high harmonics of the rotational periods of asteroids at 4 or 5 hours. I can't give you an exact noise curve for this because, of course, this depends a little bit on how exactly the asteroid is moving around. But this is the sort of frequency ranges that you're going to start worrying about the rotational motion of the asteroid getting in the way of making a measurement here. And so you might get some access to, say, the gap between the fundamental and the first harmonics. But because you have one asteroid, say 4 hours, one at 5 hours, and actually it's not 4 and 5, it's like 4 point something decimals. These are not going to be commensurate periods, and so eventually these harmonics are going to sort of blend into each other, and you'll find it quite hard to find clean frequency bands to make this measurement. So the higher frequency sensitivity gets cut off by the rotational motion of the asteroid. The other thing you might worry about as well is that for an asteroid like Eros, actually, because of the fact that it has the sausage or cigar shape, it has 3 different principal moments of inertia. It's actually rotating around the largest one, so that's actually the stable rotation, but it can wobble, just torque-free Eulerian rotational motion causes it to wobble. That wobbling has been bounded at 10 to the minus 3 degrees. It's expected to be at about the 10 to the minus 4 level. That would actually be a much larger noise than you'd want for this measurement. It'll give you a noise sort of up here in strain. So that also might window out some additional periods at lower frequencies here as well. But the wobble period for Eros is actually 15 hours. So that's still only above 10 to the minus 5 hertz. So it might put some additional narrow frequency bands into this region down here where you have to worry about rotational motion. But it's not going to block out like an order one fraction of this band. It might just sort of window out some additional frequencies you can't look for gravitational waves very well at.
Sorry, can I say one more word about what is harmonic?
Oh yeah. So think about let's say I have an asteroid rotating which has got a perfectly uniform surface albedo, but it has a weird shape. Okay. I would expect naturally then that I would see a modulation of the orbital period of the asteroid, right? Because it has some weird shape. Now, assuming you paint half the asteroid black and half the asteroid white, you would expect to see an additional noise at the first harmonic now, because now you have something which has got a fluctuation which is now at sort of twice, or maybe you don't do half, maybe I think you have to do it by quarters. So you paint like 2/4 of the asteroid white, 2/4 of it black. There would be an additional higher frequency noise component now because you have something spinning, but there's also an additional surface fluctuation that you see on the asteroid itself. So you would expect perturbations at high harmonics of the rotational period as well. Okay, you might wonder why I cut this plot off at 10⁻⁷ hertz, because if you compare the red line and the pulsar timing range, you think there's still a big gap here. But it turns out there's another noise source here, which was underappreciated until we pointed it out in a separate paper last year. So this sort of came out of this project, was a separate piece of work pointing out the existence of a new noise source for gravitational wave detection in space. So I won't have time to give this its full justice because this is another talk in its own right. But the idea here simply is that forget about the fact that I'm using asteroids as test masses for this talk. Think about any two test masses, test mass 1 and test mass 2, sitting here in the inner solar system, moving around in some circular orbit inside the inner solar system, and you're trying to measure the distance between these things as a gravitational wave detector. Now, of course, those test masses are going to respond to any gravitational force that acts on them. And in fact, you can't and you wouldn't want to shield gravity of your test masses for a gravitational wave detector. So you have to take the gravitational environment that you find. Now, of course, these test masses are going to be perturbed by things like other planets in the solar system, other moons in the solar system, but those are big objects whose masses are pretty well known, as are their positions. What is much less well known, though, both positions and masses, are the positions and masses of the other million or so asteroids in the solar system, which are sitting in the main asteroid belt. And so at some level, you will not be able to fit out 1 million individual waveforms in your data stream and still be able to make a confident detection of a gravitational wave below a 1 million parameter fit, or actually a 6 million parameter fit, because there have to be 6 individual, even if they're on elliptical orbits, there's 6 individual parameters for each orbit, plus a mass. And so these things will essentially at the level that you pick up this noise, that's just tickets for gravitational wave detection, right? You can't go below that. So we did a very careful series of modeling work in this paper that came out end of last year to actually point out how large this noise source is. And this is the result for that for a 1 AU orbit with a 1 AU baseline between the asteroids. And so basically we translate this noise into a noise for our proposal here using these asteroid test masses. I'll just remind you, this asteroid test masses, asteroid GGN, sort of accidentally have got asteroid in the name, but they come from different sources, right? The asteroid test masses are things that we're using for the detector. The asteroid GGN just happens to be the other noise source. And so the asteroid GGN on my asteroid test masses gives you something like this blue band and blue line up top here, which very sharply cuts off your sensitivity at low frequencies. This is actually an exponentially fast function of frequency down here at low frequencies. So you hit a noise wall below 10⁻⁶ hertz, which cuts off your low frequency sensitivity. Okay. Another thing you've got to worry about, this is more sort of asteroid selection criterion than it is actually a problem, is that you can have magnetic torquing on your asteroid because there's a magnetic field in the solar system. It fluctuates, there's the power spectrum. And if the magnetic moment is too large, that can cause a torque motion on the asteroid, which will give you a noise source. It turns out that for the specific magnetic moments that have been measured for things like Eros at 10⁻⁶, if you translate what this magnetic field fluctuation looks like on the torque in terms of a strain noise, you get projections which are much lower than this gray band here, which is the lines I've been showing you so far, basically. So that would be a subdominant noise source. But for other asteroids, something like Gaspar and Braille, the magnetic moment is actually much larger, and that might start becoming a noise source. So this is more a asteroid selection criterion than it is actually a noise source. We just need to make sure that the asteroid you're looking at doesn't have a very large magnetic moment, which could be messed around by the fluctuating HMF. Okay, seismic noise. Unfortunately, I can't give you a careful estimate for seismic noise because it's never been measured on an asteroid. The reason it's relevant again is because your base station is on the surface of the asteroid. That's a proxy for the center of mass of the asteroid. And of course, if the surface fluctuates seismically, that's going to mess up your ability to detect the strain. But there are reasons to be hopeful here. There are a number of reasons to be hopeful here, actually. So firstly, we know seismic noise on the Earth is a very, very bad noise source. But of course, asteroids are not the Earth. They don't have molten interior. They don't have oceans flopping around. They don't have humans walking around, hopefully. And so, the seismic environment is very different on the asteroid than it is on the Earth. It's going to be much quieter on the asteroid. And asteroids are perturbed by heating and cooling on the solar cycle and also occasional collisions with dust. And that might have some effect that causes seismic motion of the asteroids. The thing you'd be really worried about there, though, is if there was some, normal mode motion of the asteroid that could be rung up by an external perturbation on the asteroid. So let's say I could whack the asteroid with a hammer and it rang very strongly in the 10⁻⁶ to 10⁻⁵ frequency band. That would be a problem. But it turns out that you can actually do normal mode modeling of Eros. People have done this for other reasons. And the lowest normal mode frequencies you find are actually way above the band we care about. They're at 10 millihertz. So you don't get that sort of strong ringing motion for asteroids in this range. which is not to say that there's no motion of the asteroid. It's just that it's not going to be this time of ringing. The kind of thing you're thinking about here is sort of some sort of longer term plastic deformation or some sort of tectonic-like motion of the asteroid surface. But again, I can't give you a strong estimate for that because no one's ever measured this on an asteroid. It would need to be something that would need to be done as sort of a stepping stone to actually making sure this mission could work, is measurements of this type, both seismic motion on asteroids and also this longer term plastic deformation drift of asteroids would need to be nailed down more carefully on future missions. There are already some ideas to do this because this tells you about asteroid internal structure as well. So this adds to the science case for doing those. The other thing to say, of course, is that the two bodies in the solar system other than Earth where seismic motion has been measured on the Moon and Mars, and on both, and the Moon is during the Apollo missions, Mars actually very recently. The amplitudes of the seismic motions you're seeing there are typically a nanometer, but that's for a seismograph, which is most sensitive near a hertz. But if this were the amplitude of the motion you're talking about, that gives you a strain of 10 to the minus 20, which would be low enough for us. But of course, this is the different frequencies, so you can't make a direct comparison here. There are reasons to be hopeful, but again, this is something which would need to be measured and pinned down more carefully before you would fly a full mission of this class. So
yeah, so just to understand, asteroids, unlike Earth, right? We don't have power source for them to have assessment.
oh, but you have external perturbations like dust that
Yeah,
fluoresce with, right?
So like the sun hitting the different part, the different, yeah, they wobble around. So in principle, the form should be the same as the harmonics you were calculating. In some sense.
Yeah, unless somehow like you have nonlinear response, right? You can crack the asteroid, then it moves, something like that, right?
The question is, it should be, usually it should be on the same form as the other noise you calculate, but you're worrying that the asteroid may be accumulating some more and more energy in that because it's some resonant mode for that. That's.
But you can't because they're not in the band you care about. Exactly.
Yeah. Okay. So I see. So you don't know, but you think they're not in the band.
Yeah. This is sort of a series of statements that I think are making us think that seismic noise won't be a problem, but making the actual estimate was not something. We have not made the actual estimate yet again because I mean no one knows what it actually is. You need to go and measure this. So I think the conservative way to say this is that this is something which you would worry about. You would need to measure this as a sort of preliminary mission before you actually deploy the full mission of this type.
But what about something like having some snowball, these comets that are like snowballs, they have water as they get close to the sun, there's ejecta that come off of it. So again, that's probably a selection.
Yeah, you wouldn't pick a comet for this. You'd pick an asteroid, which that doesn't happen with.
So there's nothing on these asteroids, they're pretty clean. That's the idea.
Yeah, the ones you would pick would be pretty clean. Like Eros doesn't throw stuff off its surface. Bennu does. I mean, Bennu, the reason it throws stuff off its surface is I think the rotosphere actually sits slightly inside the surface of the asteroid. And so if a rock rolls down the surface of the asteroid, when it gets to the equator, it's actually spinning fast enough that it can just get thrown off into orbit. So they actually found it by just that, like orbiting this asteroid, when actually they landed on it. So you wouldn't pick things like that. But again, it's sort of it's a selection criteria on the objects you want. So that sort of brings me to the conclusion of this part of the talk about asteroids as test masses. So other than those few caveats that I've given you, which are things which we would need to still measure, the picture here looks very bright. There's a huge amount of parameter space here that looks to be accessible using asteroids as test masses. Let's say over 2 orders of magnitude in frequency and a couple of orders of magnitude in strain. That appears to be accessible using this idea of using asteroids as test masses if you can actually exploit them. So that's a pretty cool observation. I think this is really exciting because this is another way of getting into this band using a natural astrophysically massive object, which you don't have to do the engineering for to actually build the object. It's already there. So I'm probably running a bit late, but I just want to say a few words about the ranging system now as well. So unless there are any questions about the asteroids as test masses.
Yeah, just don't worry about time.
Okay. Okay. All right. So for the last couple of minutes of the talk, I want to spend just say some brief words, sort of very conceptually about the ranging system. We have kicked around more technically precise ideas than this, but I want to give you sort of the conceptual picture here because actually deciding on one form or another of actually implementing this ranging system would be sort of the realm in which a technical design study would really be required to actually assess like what actually is technically engineering feasible. But I just want to give you some words showing you like the class of ranging system and the class of clock system you need and how the sort of the rough requirements that you would need to be able to link these asteroids together. I'll say some words about some of the sort of the slightly more technical implementations of this as well, but I'm not going to dwell on that particularly. So the first thing I want to think about is actually just the ranging directly. Can you send pulses back and forth between these asteroids? Like, what are the requirements on that system? So let's think about doing laser ranging between asteroids. This is one of the two ideas we thought about. Radio ranging is the other one. So the idea here is that your spacecraft or your base station consists of some laser and some telescope of diameter d, which you're going to point toward the other asteroid. Now, this is maybe one of these things where you want the base station that actually has the telescope to be in orbit around the asteroid, so that you can, have your telescope pointing in some direction, and it's quite easy to slew it around. Slewing around a telescope that's actually, landed on the surface of an object might be more difficult than doing it when you have a telescope just sitting on some satellite in space. The reason you still need the asteroid in that case, of course, is because your satellite's going to be kicked around enormously by all the environmental noise sources. So you need a second system then to say, I'm going to reference the satellite position using, say, a separate laser ranging system to a series of reflectors or corner cubes that I put on the surface of the asteroid that allows me to then measure where the spacecraft is relative to the asteroid surface. And then I measure distance between the spacecraft, but I can back out the asteroid center of mass motion, making all those measurements at the same time. So you have this telescope of diameter d pointing at the other asteroid. And the idea is that base station A sends out a pulse. That pulse travels toward spacecraft B. It sees the pulse has arrived. I'm going to make the assumption here that all you require to see the pulse has arrived is that you receive one photon from the pulse at the frequency that you sent the pulse out at. And you can say, aha, I saw a pulse because I saw a photon. And then the base station at B says, I saw a pulse, so I'm going to send a powered pulse back to asteroid A. Asteroid A then sees, I saw one received pulse back from asteroid B. That must mean I saw the return. And so I can time this amount of time that it took for me to send the pulse out for it to come back. The reason you need a powered return pulse, of course, is if you just rely on passive reflection, you lose way too much power here. And so if you just think about this and you think about asteroid A sending out this continuous train of pulses, once every time delta t, you pulse the laser on and off for amount of time delta t. And maybe you encode on top of this some sort of digital code, so you know exactly which pulse you're talking about when, and you can unambiguously identify them. Maybe you like 3 on, 1 off, 3 on, 1 off, something like that. And then what you just do is you take all of these timing measurements and you try and figure out how well you can actually measure the gravitational wave strain. The estimate here is that the strain measurement you can make is the timing sensitivity you get over making this measurement over a full gravitational wave period divided by the baseline distance L. And the timing accuracy, because you're receiving one pulse per, you're receiving at the distant end of the baseline, one photon per pulse. You can locate each pulse within the width of the pulse, an amount of time delta t, and you have n pulses, so you get to win by square root n on the number of pulses you have. And the number of pulses you have is given by the length of the gravitational wave period divided by the pulse duration. So putting all this together, you get a parametric estimate for what the strain sensitivity is if you know what the gravitational wave frequency is and what the pulse duration is. Now, you can't just put any arbitrary number in for the pulse duration because your telescope has some Rayleigh range associated with it, your laser and telescope system, which causes the beam to diverge beyond the Rayleigh range. And you need to make sure you do receive at least one pulse far into the baseline. And so that puts a restriction on parameters of the laser, like the laser power, the telescope diameter, and the pulse duration, such that you will receive at least one photon on the far end of the baseline. So when you put this together with this, you can find an estimate for what kind of system you require to see gravitational wave strains at a certain level. When you do this, just to add one more line to the series of plots, you can get, let's say focus on this dashed line up top here to start off with. This was assuming a 1.5 meter diameter telescope and 1 watt of laser power. So 1 watt of laser power is a fairly typical amount of power you can assume for sort of on orbit things. And a 1.5 meter diameter dish is not enormous. It's not the smallest telescope that's ever been put in space, but it's not a. The point here is this doesn't require you to have a gigawatt of laser power and a 100 meter wide telescope, right? This is a relatively reasonable optical system. It's a 1.5 meter dish. It's 1 watt of laser power, and you can then get access basically to most of this region where asteroids are sufficiently good test masses. If you allow yourself a bit more power, a factor of 3 more power improves this by a factor of 3 to the power 3 halves, which is about 5. And then you can get basically access to this entire range where asteroids are good enough test masses. So this sort of conceptual idea of a telescope and a laser sending pulses back and forth between the baseline appears to have enough sensitivity to make this measurement over most of the range where this is a good set of test masses. Just to make the point though, we're making a measurement which is much, much, much worse than LISA at high frequencies, right? LISA does incredible accuracy on their relative measurement between the test masses at high frequencies. We can relax a lot of this because we don't need to make a measurement as precise as LISA, because A, the absolute measurement that you require here to get the same strain is smaller because you have a longer baseline, and you have longer to make the measurements. You don't have a system which can make the measurement as good as quickly. So you can get away with a couple of orders of magnitude worse optical system, which is also to say we're not in competition with LISA here at all, right? So LISA is a much higher frequency. We have a bunch of reasons why you can't push out to higher frequency and overlap with the LISA band. Okay, so this is sort of at a conceptual level at least, the link appears to be require parameters which are not too difficult to achieve. The other thing, of course, you require is a good clock to make the timing of the round trip of the pulse. So the way this works is because you're sending out a pulse from A toward B and then back toward A, so asteroid A starts their clock when they send the pulse out, and they stop the clock when it comes back. Now, if you think about running something like a cold atom atomic clock in space, the idea here is that between this point over here, when you emit the pulse and when you receive it again, the amount of phase, and I've left out a factor of 2 pi here, so these phis are all modulo 2 pi, or it be divided by 2 pi, should I say. The amount of phase your clock picks up is basically the nominal tick time of the clock, if there's no gravitational wave, which is twice the baseline distance, times the frequency at which the clock is running at that time when you actually are running this, amount of time to have the baseline. Now that frequency is the nominal frequency which the clock ticks plus some error term, which is some frequency drift of the clock, because it's never running precisely at an atomic clock frequency, right? So if I just do 2 measurements of the same baseline distance on the same baseline with no gravitational wave, I'm going to find a difference in the amount of phase I measure between any 2 such measurements because the frequency of the clock is going to wander around a little bit between those 2 measurements. So there's a noise source, which is the frequency wobble of the clock, which is the thing I'm going to be trying to fight against here. You've got to compare this to the size of the gravitational wave signal. So the number of extra clock ticks that you get if you make the measurement, say, right here, where the gravitational wave has got a maximum amplitude in its waveform, and then right here, where it's got a minimum amplitude, and you compare how big the timing difference is between these 2 points in the gravitational wave, you find it's twice the baseline distance times the characteristic strain, and the phase you pick up is running at the nominal clock frequency, is sort of the leading order term here. There's also a suppression effect once you're inside the baseline, but that's sort of a separate effect. And so the idea is you're trying to pick up this signal over this noise. So you compare these 2 things to each other, and you find that the strain noise you pick up, except for this correction factor, which has to do with geometrical factors about the baseline, is basically directly the fractional frequency stability of the clock over the gravitational wave period or half period. Okay, so you need a clock which is as accurate in frequency stability as the strain you're trying to measure. Now, happily, such clocks do exist on the ground. So if you look at the world leading cold atom atomic clock that's run, this is the GLS strontium optical clock. Here are their frequency stability measurements actually that are made in the existing clock. This is from this paper down here. This is Jun Lee's group. So you'll see here that the fractional frequency stability of this clock running over 10 to the 4 second integration times exceeds 10 to the minus 18. And that means that if you can just take, so of course this is a 10 to the 4 seconds, you need to actually extrapolate this down to 10 to the 6 seconds to get to a 10 to 6 second gravitational wave period. We didn't assume any further improvement beyond this. We said, well, maybe systematics limit your ability to push the clock much longer than this. So let's go down to this level and then go flat to longer time periods. I think it's a relatively reasonable thing to do. And when you do that and translate this to the characteristic strain curve, you get this salmon shape, the salmon colored curve here. Taking into account both our extrapolation flat and then this line rising as 1 over root t, and this baseline suppression factor. That's why you have these 2 breaks here. This is our extrapolation down here. This is where this baseline suppression factor kicks in over there. So this tells you that using the existing best ground-based cold atom atomic clock, you would again be able to access most of this band. But there are 2 things to say here. Firstly, this is the existing best ground-based clock from 2019. And the way that clock improvements have been happening in the last couple of decades is that there's basically a Moore's law to how quick clocks improve. So we would assume improvements over and above this by the time you actually fly a mission of this class, or at least get around to doing technical specifications of this mission. So you might get some improvement over this. But the other thing, which is actually a downside, is that this is the world-leading best ground-based cold atom atomic clock that has ever been demonstrated on the ground in the lab, armed with an army of scientists, of course. This is not on orbit. So this is something which actually would need to be space qualified to fly on orbit as a clock that's this good. Now that would require R&D, but there really is an R&D effort ongoing to do precisely this, because a lot of the technology you develop for deploying cold atom atomic clocks on orbit also has applications in these atomic midband detectors for the gap between LISA and the ground-based detector. So there's a lot of R&D crossover between cold atom clocks in space and the cold atom gravitational wave detectors. And there's already been a couple of conferences actually this year talking precisely about these technology crossovers and using this as sort of a motivating factor for going after putting clocks and these types of clocks, these cold atom atomic clocks, in orbit in order to sort of act as a technology R&D platform for eventually getting to the mid-band detectors. So we would obviously piggyback on that effort. We would require some significant R&D to get to this level, though. Current existing best space-based clocks are up here somewhere, the ones that have actually been demonstrated on orbit, but they use a different technology, so they're not called them atomic. They're not the same type of called them atomic clocks. So, you know, we would have to piggyback off this R&D effort. This is sort of one of the other things that requires improvements in the technical capabilities to actually be able to achieve this mission.
All right, so the LISA Pathfinder doesn't appear on this plot because they don't use atomic.
Oh, LISA Pathfinder was just a test mass isolation engineering demonstration.
Yeah.
Also, LISA does the measurement very differently, right? They don't do a timing measurement, they do an inframetric measurement of lasers. So they're doing a laser phase comparison, they're not doing a timing measurement.
But it didn't, you in the earlier slide saying LISA to reach there, they need to have like many other magnitude improvement on their. That wasn't a timing measurement per se. That was a rough analogy in the ranging accuracy. They're doing it very differently though. Oh, so okay, so we shouldn't say that.
Yeah, maybe I misspoke. I didn't mean to imply that LISA requires better timing. LISA does the measurement very differently. I meant they have a better relative position location of the masses at the high frequencies. Okay, so with that, I can come back to the slide that I showed you right at the start of the talk, which is the combined envelope strength sensitivity curve. So just to sum up here. So taking into account all the noise sources I've showed you, with the exception of clock noise, which I'm neglecting here, and with the exception of some of the other noise sources, which are more like selection criteria, and obviously with this caveat about seismic noise as well, but putting together all these noise curves, you get this either red or green curve, depending on what you're assuming for the link system. And I think it's a pretty exciting set of results, because this is showing you that asteroids are excellent test masses to access this microhertz band between, say, a microhertz and 10 microhertz. You're getting a number of orders of magnitude improvement over other things which we have really thought about very carefully. We maybe don't quite get to this what this Muware's strawman concept was proposing, but I remind you that was at the level of a strawman concept. That wasn't actually a well-developed proposal at this time. And so this is really exciting as an alternative way to get into this band. And moreover, it looks like the kind of ranging system, just using these sort of laser ranging with an atomic clock, would be able to actually get access to most of this band as well. So both from the asteroid test mass side and from the ability to range between the asteroids, this looks like a pretty exciting set of results. Of course, this is not the end of the story. There are a couple of things that strongly motivates. The first one, of course, is doing a detailed technical design study, right? This is all conceptual level stuff. You need to actually check now, can you actually engineer and build the objects you actually need to do to actually build this mission? And what are the requirements to do that? The other thing, of course, is these in situ seismic measurements would be really important. And then the sort of other big one is getting the space qualified atomic clocks going. But both of these things are already motivated from other reasons as well. So we hope to piggyback off those efforts as those get developed over time as well. So with that, I say thank you very much for your attention, and happy to take any questions.
Yeah, thanks.
Yes,
Yeah,
just,
questions.
one final question here. So this is all great. You've shown that there's a nice window there. So then give me a time estimate. If everything goes well, when can I expect like a launch, something like this?
Yeah, I can't really give you a time estimate. I don't know what the answer to that is. I mean,
like at least 20
it's
years.
decades, right? It's not going to be. I mean, think about LISA's timescales, right? LISA has already been spec'd out. The technical design study has been done. A lot of the R&D has been done, and that's already still launching in mid-2030s, right? So early 2030s. So we're talking about sort of mid-century type timescales, I would think.
Okay, I'll keep that in mind.
I'm sorry,
I'll keep that.
Maybe not quite mid-century, but I wouldn't say, yeah, maybe mid-century is too pessimistic, but probably 1 or 2 decades is probably the minimum timescale we're talking about here. Something like that.
Good, yeah, that's good.
Sorry, if I use the available atomic clock on Earth, that suddenly I can ship it to the asteroid. That's the only technical limitation, right? What are the other technical limitations?
I think the other technical limitations would be, how exactly do you implement the link system? Okay, so I've told you 1.5 meter laser, the 1 watt laser with a 1.5 meter telescope is good enough, but like, I don't know exactly what the technical engineering R&D would be required to actually realize that. There may be some additional issues which you can most likely mitigate by like the spacecraft stability and stuff like that, but you can do real-time metrology of the baselines and stuff on the satellite. So But it's basically the engineering study now that goes into this to say like, okay, this is what you need to do. How can you do it? How much does that interfere with your ability to actually achieve this?
And more people in the sense that, when the countries compete with each other, they always want to compete in space missions. So as you can do some prototype, I'm sure some country, if they decide to pick either they pick quantum or pick space.
Exactly right. I mean, there's this call that Clarkson space thing is one of these quantum metrology things, right? So there's a lot of support behind that as well.
Yeah, I mean, it'll most likely probably might be earlier, actually. It's probably
Yeah.
more on the early side than say mid-century.
Yeah, I think I agree with that. But I mean, space missions always take a lot of time to actually build, and there's always inevitably delays and things like that, right? So I mean, I'm obviously not technically qualified to tell you when the space mission is going to launch. It's way above my pay grade. But I think this points out the feasibility of doing this.
Exactly, yeah. That's right. Yeah, the physics case is pretty strong.
No questions?
We should check.
Yeah,
Seems like no questions on the.
I have a nice question. So since the mass of that body is important factor here, why don't you consider something bigger than a normal asteroid like Pluto and Vesta, for example?
Right. So Vesta is in the asteroid belt. So this gravity gradient noise estimate that I told you, this is the noise estimate when you're talking about inner solar system asteroids, which are an AU away from the asteroid belt. If you're actually in the asteroid belt, it's way, way, way worse. So you can't use it in the asteroid belt. That's where Vesta is. Pluto, sure. I mean, potentially, yeah. You've got to worry about planets, whether or not they're active in any way.
I think Pluto is not safe. I think, yeah, okay. I don't know. I don't think anybody knows, right?
Exactly right. So this could be like the Jovian moons where you have like
But there is
streams of gas giving
some
volcanoes.
close by flying by, right?
Yeah.
And there's some indication of maybe recent seismic but I'm not sure. But I heard some news like that. Yeah. Okay.
Yeah, exactly. So I mean, I think there's a limitation of going too large on the object, so it takes you to potential, on-body noise sources. But that said, I mean, like the seismic environment on Mars, where is that plot? Sorry, I've lost it now. This is very quiet, right? You wouldn't necessarily expect Mars to be that many more spatially quiet on the Earth, but it is, because it doesn't have this molten core at the same level the Earth does. It may still have some molten core, but it doesn't have this sort of same tectonic motion as the Earth does.
Because Venus is the complete opposite.
Yeah, exactly. You may think about using one end of the baseline as like a moon. So we thought a bit about using our moon
For
as,
example, our moon and Mars. So Mars, Pluto, and
or our moon and Eros.
Okay.
One end of the baseline is an asteroid, one is the moon. One of the problems there, I'm not sure it's a problem so much as one of the sort of challenges, is that the rotational frequencies of the moon are here. So right at the band you care about. So that might be a challenge. I'm not sure to what extent you can model that out. The moon is not rotating in a 4 to 5 hour period, right? It's like 30 days. So, you're sitting with bands which are sort of uncomfortably in this region where you actually care about making the measurement. You could, for instance, use Phobos and Deimos, which are Mars's moons, other rocky objects in the solar system, if you can't find asteroids that work. Yeah, I mean, I think that there's a broader class of things to consider as test masses here. Planets might be tricky though, but other asteroids which are not in the asteroid belt would be good things to look at.
Planet 9.
Planet 9 is gravitational wave detection. Now there's a title for a paper.
Okay, so if there are no more questions, then let's.
Sorry about the time.
So your detection mechanism is putting a spacecraft flying past this asteroid and